On this worksheet, we're going to be reviewing general chemistry, hybrid atomic orbitals. Let's start out by drawing an S orbital. An S orbital, if you recall, is just a spherical orbital. I'm drawing it as a circle, but this is a three-dimensional sphere, and the dot in the middle is the nucleus of the atom. A p orbital is the one that's shaped kind of like an infinity symbol or a figure 8, with the nucleus in the center right here. So that's an S orbital, that's a p orbital. We also learned about d orbitals in Gen Chem, but we don't really talk about them in organic. Let's complete this table that has to do with hybrid orbitals. First, we're going to draw a hydrocarbon that has 2 carbon atoms and an appropriate number of hydrogen atoms that illustrates sp3 hybridization. So we want 2 carbon atoms, and we want as many hydrogen atoms as necessary so that we have sp3 hybridization on our carbon atoms. So in Gen Chem, this is kind of like backwards from how we learned it in Gen Chem. In Gen Chem, when you were learning about hybridization, you learned to look at a molecule like, let's say we had NH4 positive charge, ammonia, and we wanted to know what the hybridization was for the nitrogen atom. You learned in Gen Chem that you do this by counting the areas of electrons around the nitrogen. This nitrogen has 4 areas, and we talked about how we need 1 orbital for every single one of those areas. Since we have 4 areas, we need to have 4 orbitals. That's going to be an S and a P and another P and another P. That's going to be sp3. So the number of areas is what dictates the hybridization. And in Gen Chem, that's how we approached it. You looked at a Lewis structure, you counted areas of electrons, and you came up with hybridization. In this situation, we're going to go backwards. We're looking at the hybridization, and we're going to use that to draw the molecule from there. So this hybridization, sp3, means that we used an S, a P, and a P, which means that we have 4 areas of electrons around each one of the atoms in this molecule, each one of the carbon atoms in this molecule. And as it's drawn right now, the carbon atom on the left has 1 area of electrons, so that means we just need to give it 3 more areas of electrons, and now it's sp3 hybrid. Same with the other carbon atom on the right-hand side. This is telling us that we need 2 carbon atoms and an appropriate number of hydrogen atoms, so that means all of these empty bonds I'm just going to fill up with hydrogens, like that. And it asks us what type of bonds are possible for carbon atoms that have this type of hybridization. That carbon atom has only single bonds. When a carbon atom is sp3 hybrid, its only option is 4 single bonds. Now we're going to do the same thing with an sp2 carbon. So we want to have our 2 carbon atoms in this molecule. sp2 hybrid, that means that we mixed 1 s orbital with 2 p orbitals, which means that we need 3 areas of electrons around each one of these carbon atoms. We've already got 1, so we're going to give it each one of them, we're going to give 2 more. And now each one of these carbon atoms have a total of 1, 2, 3 areas of electrons. We're going to fill in an appropriate number of hydrogen atoms. So that means we're just going to be filling hydrogen atoms in on these empty bonds. And we've got that right there. Now we do have a little bit of a problem. Don't forget the Octet Rule, which says that every atom needs to be surrounded by 8 electrons. Right now, we're only surrounded by 2, 4, 6 electrons. So to give it the 8th electron, we're just going to bring a double bond in. We're totally allowed to do that, and hopefully you kind of got that hint over here. With a double bond in place, we have 1, 2, 3, 4. 4 bonds, we have 2, 4, 6, 8 electrons. So if a molecule that has a carbon atom that's sp2 hybrid, we can see from this picture right here that it's going to have double bonds. It's also going to have single bonds. 1 double, 2 single. And then last but not least, sp hybrid. So here's our 2 carbon atoms. Sp hybrid means this came from an S and a P, which is 2 areas of electrons. And right now each carbon has only 1 area. So we're going to give each one of those carbon atoms area number 2. The carbon atoms only have 4 electrons. That means they need some more in the form of a triple bond. Sp hybrid, this would come from a triple and a single Another option for sp hybrid that we're not drawing on this worksheet would be 2 double bonds. We're not showing that here. It's not possible to do that with carbons and hydrogens, but here is an example of an an sp hybrid carbon that has 2 double bonds. Okay, now what we're going to do is rank bonds single, double, triple from weakest to strongest. The single bond is the weakest, and the triple bond is the strongest. And for your explanation, typically what students will say, it just has to do with the number of electrons that are in each of these bonds. The single bond has only 2 electrons in it, whereas the triple bond has 6 electrons in it. When we're ranking the bonds in terms of weakness or strength, what we're specifically talking about is how difficult is it to actually pull the molecule apart at that bond. Like, how hard is it to separate the atoms that are bonded together? And the harder it is to separate them, the stronger the bond is. So the logic is that if you have 6 electrons that are holding atoms together, it's going to be really hard to pull them away from each other because there's just a lot of electrons there that are trying to hold them together. And if you only have 2 electrons between a couple of atoms, it's going to be a lot easier to separate those atoms from each other. And that's a super logical reasoning. Like I said, that's the one that students usually prefer to use because it makes sense. Now we're going to rank bonds in terms of length. We did talk about this a little bit in Gen Chem. It's not super intuitive for a lot of students. The single bond is the longest bond, and the triple bond is the shortest bond. And we don't really talk about why this is the case in Gen Chem, so a lot of times at this point, students are kind of floundering, like, how am I going to explain the ranking of this? Why would the triple bond be the shortest bond? Sometimes students just want to kind of default back to the 6 electrons versus 2 electrons argument and say there's a lot of electrons inside the triple bond, so it's just helping to pull those electrons together. I'm going to kind of not address that yet. We're going to go to the next page. So the next thing that we're going to do, but don't worry, I am going to come back to this. So the next thing we're going to do are draw these hybrid orbitals, drawing hybrid orbitals. And you might remember doing this from Gen Chem, you might not. An sp3 hybrid orbital is an orbital that is 1/4 s, we say character, and 3/4 p character. This has to do with the fact that it's made by combining 1 s orbital with 3 p orbitals. A total of 4 orbitals, all coming together. One of them is an s orbital, and 3 of them are p orbitals. So an sp3 orbital looks a lot like a p orbital. It's 75% p orbital. And so it has a shape that's pretty similar to the dumbbell shaped concept. But if you remember, it's not like a perfect symmetrical figure 8. It's got like a weird kind of stubby lobe on 1/2. And here's the nucleus right here. So it's like this asymmetrical p orbital that's only elongated on one side and the other side is kind of stubby. So now we're going to draw an I'm going to label it, that's my sp3. Now I'm going to draw an sp2 orbital using kind of the same logic. An sp2 orbital is an s with 2 p's, which means that it's 1/3 s and it's 2/3 p. So it's still mostly a p orbital, just not quite as much. So when we draw an sp2 orbital, we want to make it maybe not quite so elongated, more p-like, or excuse me, more s-like. Remember, the s orbitals are kind of round, spherical. So what I'm trying to draw here is something that is rounder, like when I'm looking at, let me highlight here, I'm looking specifically at this part of the orbital. So I'm wanting to draw something that's rounder and longer. I feel like I did, or shorter, I mean. I feel like I did an okay job. I want this lobe to be more spherical, not perfectly spherical, just more spherical, and also a little bit shorter to just kind of match the shape of an s orbital. So that's my version of an sp2. And then an sp orbital, by the same logic, that comes from 1 s and 1 p, so that means it's 1/2 s and 1/2 p. So when we draw an sp Sp orbital, let me give my nucleus here, we want it to be even stubbier, even rounder, like that. So I'm going to erase that, and I'm going to highlight over here. So looking at that portion that I just highlighted, I want that portion to be even shorter and rounder. I feel like I did a decent job. If you like look at pictures that are in your book or on the internet, they're going to look way better than what I just drew. Okay, so we've got those hybrid orbitals drawn. Now what we're going to do is rank them in terms of their length, from shortest to longest. When we're doing this ranking, like kind of the easiest way to do this is to start at the nucleus and then look at the distance to the outside of the longer lobe. So we're comparing these lengths right here. And in that logic, this one right here is going to be the shortest. And this one, the Sp3, is going to be the longest. And our explanation for that is because the shortest, the Sp orbital, is 50% S. And the S orbital is just a sphere. It's a round little sphere. The longer orbital is long because it is 75% P, which is that long figure 8 shape. Right? So the different lengths have to do with how much S character, if I'm going to use that word, how much S character is present in the orbital and how stubby that orbital ends up being as a result. So maybe I'll add over here, it's only 25% S, which is the short and stubby orbital, like that. And this is 50% S, so that S character is more pronounced in that orbital. So now, what is the relationship between bond length and hybrid orbital length, which was talked about in question 6 that I just kind of skipped over? In question 6, that was talking about the length of the single bond, the double bond, and the triple bond. And you just sort of learned in Gen Chem that the triple bond was the shortest, and the single bond was the longest. And we didn't really spend, we don't spend a lot of time in Gen Chem talking about why. That has to do with these orbitals. So I'm actually going to copy a couple of these orbitals and bring them down here. I'm going to actually bring 2 of them down here, and I'm going to turn them around. And then I'm going to do the same thing with the Sp orbitals. And so what we're going to do is sort of imagine these orbitals kind of coming together and bonding. So let's say that this is a carbon atom and this is a carbon atom, and these 2 carbon atoms are Sp3 hybridized, and they're going to come together and bond. And in order to do that, they have to come together so that these orbitals like come in contact with each other and overlap a little bit. Like we'll just put them in contact with each other. And when they come in contact with each other like that, then the bond is formed, and the bond length is defined as the distance between these 2 nuclei. So there's our bond length right there. Now we're going to do the same thing over here. These are a couple of Sp hybrid carbon atoms, and they are going to also come together to bond. This is going to be to ultimately make a triple bond. So they're going to come together, and remember, in order, I'm actually going to move them down here. In order for this bond to form, these orbitals have to come in contact. So because these Sp orbitals are so stubby and S-like, they're actually the atoms actually have to come really close together to get that contact, to get that interaction. So this is what we end up with, and here is our bond length. This would be a single bond, and this would be a triple bond. Now this picture is pretty dramatic. The relative size between a single and a triple is not as dramatic as what I've drawn here, but you can see that because the single bond is being formed by long orbitals, the atoms in a single bond are able to stay really far apart from each other, and that causes us to have a really long bond length. When we're forming a triple bond between a couple of Sp orbitals, because those orbitals are really short, those atoms have to get really close together in order to actually bond, which results in a short bond length. So going back to this question, which, you probably didn't really have good resources to answer this question at this point. The reason that the triple bond is the shortest is because it is formed from short sp orbitals. And the single bond is the longest because it is formed from long sp3 orbitals.